Blender's geometry nodes is a versatile powerhouse of tools. If you know how to use the different nodes and you understand the data types, the node types, the socket types, and everything in between, you can create literally anything that you can imagine. It's continuously growing every single day, so right now is the best time to start. In the previous video, we went through the different data types, the node types, the socket types, the colors that represent each of these as well. The best way to cement your understanding is by actually going through a few examples. This could be done by following along various tutorials such as all of these. However, in today's video, we're going to go through the basic data types and just use one or two examples for each of them so that you get an understanding of how to use each data type in different scenarios. So with that, let's actually go ahead and learn how to use the different data types. The one thing that I'd like to mention is in the previous video, we did not talk about this, but if you want to open geometry nodes, you can also use this particular geometry nodes tab just by tapping it, which opens a geometry node modifier window as well as the spreadsheet up here. However, you don't have to do this, and you can do this just by creating a new window by dragging and dropping from the side, as explained in the previous videos. However, let's create a new geometry node tree, and the first data type is the geometry data type, which is represented by a turquoise color. Now this represents the input data that's going in as the output data. We are only going to be changing this data. Now, what does this input geometry data type actually contain? It contains the fact that it's a mesh with 8 vertices, 12 edges, and 6 faces. But it's not just that. It also states within the vertices different attributes like the position, the edges, the faces, as well as the face corners. So for the vertices, we have the positions and the X, Y, Z values for each of these positions. Now, whenever we make changes to this geometry, we actually change what is stored over here. So right now, this is what's being output. And that's how Blender knows that it has to render out this particular cube, because it knows that there are vertices at these positions, there are edges that are connecting these vertices, and we also know that there are faces present connecting up all of those edges, as well as the face corners, the UV map that makes this up. So for the time being, let's go ahead and just change this. Instead of having these positions, what if we have something else, our own geometry? So let's search for an icosphere and then simply plug this in to the group output. Now this icosphere geometry actually consists of 12 vertices, and we have the indices of the vertices and the positions for all 12 of those vertices. Similarly, we have the edges, the faces, and the face corners as well. But let's just look at these vertices. Now there are 12 of them numbered from 0 to 11, and that is what Blender is outputting. But what if we want to have this and this? So in order to make changes, what we do is we add in different operators that work on geometry. So let's search for the join geometry. Now this join geometry is simply going to add whatever data we had of this onto whatever data we have over here. So right now we have this. If we were to simply plug this in, you can see that after this, we also added in all 12 values that we had for the icosphere. Now that is being added in after the group input, which was these first 8 vertices for the cube. If you want to switch this over, we can actually control the order, and now it's adding the group input after the icosphere that we have over here. So now we have all vertices, the 8 from the group input and the 12 from the icosphere, coming in together to form 20 vertices over here. Now, even though we have all 20 vertices, we can't actually see them because the icosphere is present within the cube. And you can actually see that if we were to just switch on X-ray vision, and you can see the icosphere is present within the cube. You can also see that by switching over to the wireframe view, just like that. Now, let's say we want to actually move the icosphere out from within this particular cube. The way we do that is by pressing Shift A and searching for a transform geometry. Now, what is this transform geometry going to do? The transform geometry is simply going to take these position values and change them based off of what input we give. So right now you see we want to move it on the y-axis. So if we were to change this y, you can see all of the y value positions are just being updated. So we can change that to be whatever we want. Now that is essentially what all of these transform geometries and the joint geometry and things like that are doing. All it's doing is just changing the values that we have stored within this particular data type. Now, that looks really cool, and I hope that gives you a good understanding of how we use the geometry data type and what exactly the data type is. It's just these numbers present or the data present for each of the geometries. And every time we use any operation, all we're doing is changing the values over here. Some things like the joint geometry is just going to add in some values, and sometimes something like the delete geometry is going to remove some of these values. But that is all that it's doing. And with that, we actually come to the next type of data type, which is the integer data type, which is denoted by this lime green color. Now, as we stated, integers can only be whole numbers. So as you can see, 1, 2, 3, and so on and so forth. The reason why we want these to be whole numbers is because obviously subdivisions cannot be something like a subdivision of 2.5. That just doesn't make sense. It has to be rounded up to 3 or 2. So that's why at any point of time, we would want this to only give us a whole number. Now, of course, integers go all the way from negative values to positive values, but sometimes you can actually restrict this to be within a specific range. And in this case, the subdivisions of an icosphere cannot go lesser than 1. And that is simply because it doesn't make sense to have any negative subdivisions or anything, because then it no longer would have any geometry. So the subdivision value is by default restricted between 1 and 7. And the reason why it's restricted to 7 as well is simply because look at the number of vertices. If we were to have just one vertices and we have just the icosphere, then you see it contains of only 12 vertices. However, by increasing the subdivisions to 2, it increases, but not by much. It increases only up to 42. Then if we increase it to a value of 3, it suddenly jumps to 162. The next time we increase the subdivision, it becomes 642. So clearly the rise is exponential. If we were to increase the subdivisions all the way to 7, it already becomes 41,000 points. So Blender has to actually calculate it for all of these vertices, all of these edges, all of these faces. So it will definitely slow Blender down. However, if you have a PC that can handle it, you could go even greater than 7 as well. So if we were to go to a subdivision level of 8, you can see now we have 164 different vertices. And that makes it super smooth. But also, if we were to have many of these icospheres, it would definitely slow the PC down quite a lot and make your renders very, very long. So by default, it is limited just up to a subdivision level of 7, but you can go even higher. So as you see, 9 subdivisions has 655,000 vertices. Let's just keep the subdivisions down at 1 for now. Let's take a look at another type of use case for the integers. Let's say instead of this icosphere, we actually just wanted a curved line. So let's actually remove the group input and its joint geometry and everything. And let's just take a curved line and plug it in. Let's press Shift A, search for a curved line. Now this curved line has essentially 2 points, a start and an end, which can be seen again in the spreadsheet as 2 particular points for a curve. Now, if we were to change any of these, you can see the value changes over there, but that's not what we're looking at right now. What we want to do is actually use another geometry type, which is going to take these points, and instead of having just these points, we're going to plug in some instances on every single one of these points. That means we're going to take this geometry data and plug that in to these particular points. So let's press Shift and search for an instance on points node. And now it's going to take these, find the points that are there, and then instance some geometry onto that. So let's go ahead and take this icosphere and plug that in as the instance, just like that. Now you see there are 2 instances, and the instances have certain thing. One, the position of the points, which we had seen from the original curve over here. And because this is an instance on points node, we're also adding in 2 more attributes, the rotation for every single one of the instances and the scale, which is the size of each of those instances. So that's also going to be added in as a rotation and a scale value, just like that. Another thing that we should note about the geometry attribute or the geometry data type is that it not only has to store these, you can create your own custom ones as well. So for example, we can press Shift A and search for a store named attribute, plug that in. And now if we name this, let's say attribute or ATTR, for each of the instances, there's going to be a new attribute called attr. However, we can't see that because we haven't stored it for the instances. Let's change this from point to instance. And now on the instance, you see there's a new attribute called attr, and we can choose that to be whatever number we want. So that's exactly what the geometry data type does. It just stores all of these different attributes and information about the geometry. Again, if you want more information about that, do watch the previous video released in this series. But for the time being, we have just 2 points. Let's go ahead and just change the scale of all of these down to a value of 0.1, just so that they're a lot smaller. Maybe a 0.23 is good enough. However, let's say I don't want 2 points, but I want more number of points. In that case, what we can do is press Shift-A and search for a resample curve node. Now, if we were to plug this resample curve node in, you can see we can change the count just by using this particular value. But clearly, again, just like before, if we were to have something like 5.5, it just does not make sense because you can't have 0.5 points. So it has to be a whole number, and that's why we use these integers. So this way, we can never get a decimal value as such. So that looks really good. Now we're able to create as many points as we want based off of some integer value. But we still haven't taken a look at an example for where we might use negative integer values. So let's take a look at that. If we quickly take a look at this small setup that I just created, you'll actually see that we have 2 particular cubes and they don't really line up. Let's just press Shift D, Y followed by 10 to create a third one, and you'll see that it's just not lining up. However, if we were to change this multiply value to a whole number, it's going to perfectly line up. But if it is not a whole number, it's just not going to line up. So we've set up the math in a way that it perfectly lines up every time it becomes a whole number, and that just increases the number of twists in each one. And you always want a whole number of twists. So that's why we don't want these decimal values to ever be available. In that case, you can actually just use an integer node right over here and plug that in so that now you have control over it, but it's never going to not align, and it's always going to align up based on whatever value you give over here. However, in this case, if you give positive values, it's going to be rotating in this clockwise direction. If you want it to rotate in a counterclockwise or anti-clockwise rotation, you can just change this to a negative value, and now it's rotating in the opposite direction and still lining up every single time. So that's a situation in which you might require a negative value for an integer. So that's why Blender gives you the capabilities to have both positive and negative values for integers. So I hope that makes sense. Again, this particular video might be released as a tutorial sometime later on, but as of now, if you want it, it is present on my Patreon for the different tiers. Anyway, back in the video, that should hopefully give you an idea of what integers are, why they're used, where they can be used as well, along with what the geometry data type is and how it's used, where it's used, and what exactly it does. With that, we can go into the third type of data type, which is the floating point data type. So the floating point data type is represented by a gray color, as you can see over here. It's called floating because it has a decimal point that can float anywhere within the number. So you don't have to have 1 digit before and 1 digit after. You might as well have 5 digits before and 1 digit after as well. And you could also have 2 digits and 3 digits after, things like that. It's always going to be floating anywhere within the number. But this essentially allows us to have fractional values as well, and not just whole numbers. And you would want that for anything that has to have some sort of smooth increase, such as the radius of the icosphere itself. Obviously, you wouldn't want this to be like this and the next size you have directly to be a radius of 2. You might want it to be just a little bit smaller or just a little bit larger to fit into whatever you are using. So in that case, you would want to use some sort of a floating point value. Similarly, you could have negative values for floating points as well. But again, sometimes it is limited because negative radii does not make sense. In this other example, if you didn't want it to be an integer and you did not want it to match up, you could use negative values as well and maybe have it just not line up. Maybe that is some requirement that you have. But in that case, you use a floating point value that is negative or positive. as you can see. So although floating point values are used almost everywhere, I think they're probably the easiest to understand. So let's not dive too deep into any more examples for the floating point values. That will actually bring us to the next data type, which is the vector. A vector is essentially a collection of 3 floating point values. So as you can see, even though the x value looks like it's just a floating point value, if you hover over it, it clearly states that it is a vector and not just a floating point. It's a collection of 3 floating point values, one for the x, one for the y, and one for the z. That's why you're able to control the scale on the x-axis separately, the y-axis separately, as well as the z-axis separately. So it's really up to you on how you want to use these. But let's go ahead and take a look at some more examples of vectors. One example is the location, because the location also contains an x, y, and z value. So let's actually go ahead and see that this curved line actually has a start and an end, both of which are actually vectors. So we can actually control this using the location of something else. So let's press Shift A and search for an empty plane axis, and let's just move it over here. Now, if we were to take this cube again, and instead of having the end, let's just plug this empty in right over here. And now we can change this empty to relative and use its location as the end. So now you see, no matter where we move this particular empty, the points are going to follow just like that. In fact, we can resample this curve to be even more, to have even more points. And now we could actually animate the location of the empty, and we'd get this animated just as well. And in fact, while we're at it, because we are using it, we're going to talk about the object data type. And essentially this object data type contains all of this information: the transform, the location, rotation, scale, and geometry of whatever object you place in over here. So right now we have placed the empty, but you could use a constant object. So let's say constant object, and you could just select this, let's say the empty. And now if you were to use, various different versions of this, you could just use that in over here. Anything that requires an object, you could just plug it in from this constant. Apart from that, you could also do something like using a group input node and plugging the object in right over there. So now it is selectable from here. So you could actually choose to have it go to the camera or to the empty and make it change based on your requirements or some objects later on, right from the dropdown for the modifier panel over here. However, cutting away from the small segue into objects, let's talk about vector math. So maybe we do want it to be all the way over here, but maybe we don't want it to just stop here. We want it to be in this direction, but we also want it to be twice as far as this at any given point of time. For that, we can go ahead and just use some more vector math to change the actual vector values. So instead of vector math, we can add in some values and so on and so forth, but that's not exactly what we want to do. What we want is we want to multiply this by a value of 2. And since we want that on all the axes, we can change this to scale and just scale it by a factor of 2. And now you see this only gives us the direction, and it's always going to be twice as far from that position. So that's how you can actually use vector math and things to change these quite a bit. In fact, if you had 2 empties, let's just duplicate this by pressing Shift D. You can then go ahead and just add these 2 values to give something that's always going to be pointed perfectly in between these 2 empties. So if you just do that, you can see it's always going to find the perfect midpoint between these. This is actually something called the parallelogram law of vector addition, but this can actually help you visualize it. Again, if you want to visualize the vector math node even more, you can check this video out, which actually visualizes the vector math node in a lot more detail. So hopefully that gives you an idea of vectors as well as objects and how you can use those in various contexts. But that actually brings us to the next and probably the most important data type within geometry nodes, which is the Boolean. So the Boolean is actually like a selection. It gives us either true or false. It can be yes or no. So let's say we had this exact setup where we have all of these points going straight up to this particular empty. But let's say I don't want any point that is beyond, let's say, a certain distance from the origin to actually be present. In that case, how do I prevent instancing from happening to points beyond that particular distance? And for that, we would use this selection input. So let's go ahead and press Shift A and search for a position node, which is going to give us the XYZ location of every single point. Now we can press Shift A and search for a compare node, and we want to compare if the length of this position. So let's press Shift A and search for a vector math node, and then change this to length and say if the length of this position is less than, let's say, 10 meters, only then should the points get instanced. So now you see it's always going to point in this direction, but only if the points are lesser than 10 units are they going to be instanced. If they're greater than, it's no longer going to be instanced, and it's just going to stop right over there. So that is something that I think is also really cool that you can do. However, this brings us to another concept, which is called Boolean math. Let's say I do want this, but I also want it to be present on this particular empty. So if it is below 10, it should be present, or if it is at the location of this empty, it should be present. So in order to take care of that and or situation, we use Boolean math. So let's press Shift A and search for Boolean math. So all this is doing is saying that if this is true and this is true, only then should this happen. But we want to check if this is true or this is true. So what is this going to be? This is like if the position is equal to the location of that empty. So let's press Shift D, change this from less than to equal to, and we don't want to check a float anymore. We want to check the entire vector itself. So if the position is equal to, let's say, this particular location, in that case, we do want to instance it. So let's plug this in. So now you see it's present right over there as well. So now you can just move it around and it's going to be deleted if it is greater than 10, but the last one is always going to be present. So I think that is really, really cool. But let's make this just a little bit more complex, just so that we grasp the idea of integers, positions, and also implicit typecasting. So what's implicit typecasting? We've spoken about this in the previous video, but we were probably not using the actual terms. So right now this position is a vector. We ideally can do math only with vectors. So this particular purple is going to go into a purple. Similarly, this gray is going to go into the gray. However, what if we didn't use this converter that converted this purple to a gray? If we were to plug this in, what happens? As you can see, something is happening. It is different, but we are able to actually connect this into that. So what does that mean? It actually means that the vector value is somehow being converted into a floating point value. Internally, Blender is doing some type of calculations to make this change. So if we want more control over it, we would do something just like this. But what does that mean? If we were to use something like a float and try to plug that into an integer like this, it still works, but Blender is internally rounding off the floating point value into a whole number before it gets passed into the integer. So that's called implicit typecasting. It is changing the type by doing some predetermined math without explicitly mentioning it. If you want more control, you can explicitly say float to integer and plug that in right over here. And now you have some more control over exactly how you want it to be. Do you want it to just be rounded off, or do you always want the lower value? Do you always want the higher value, or do you want to just remove the decimal values and things like that? So if you want more control, you can use these nodes to typecast them explicitly. But if you don't, Blender is going to use a default method and typecast them internally either way. However, this works with only data types that can be typecast from one to another. But now let's actually talk about the slightly more interesting use case. Let's say I want this to also determine how many points there are. That way, we can take this location of the object, plug it into the vector, and we can just see the length of that position. If we now plug that into the count, you can see that by taking this and moving it around, we actually always have uniform distance between these points. Let's actually remove this as well so that we can actually take a look at how, no matter how far you move this, the number of points changes accordingly. So as you can see, if we bring this really close, there's only very few points. And if we move it further away, there are more points as well, simply because we are changing the point based off of the length of the position vector or the location of this particular object. So that is something that's really, really cool. And it doesn't have to stop at that. You could actually take the scale and use that scale down over there so that the scale of this empty determines the size of the sphere. So you could scale it down, grab it, scale it up, and do all of those fun stuff and animate the values just as you please. So hopefully that gives you a good idea of how you can use Booleans, vectors, floating points, integers, and the geometry data type as a whole. Before we go into the next data type, which is the rotations, let's actually do one last example, which uses most of these data types that we just learned about. So let's press Shift A and add in Suzanne, which is the monkey, and create a new geometry node tree for it. Now, within this geometry node tree, let's go ahead and make Suzanne appear or disappear based off of the location of this particular empty. So let's go ahead and just drag that empty back in. Now let's press Shift A and search for a delete geometry node. So once you plug this in, you can see that all of the data has been deleted. If you were to have just this in, we have 507 vertices and so on and so forth, but adding the delete geometry just removes all of them. But let's not remove all of them and use some Boolean value to delete only a specific number. So let's delete it based off of the x-axis position of all of them. So we have the empty, which is present right over there, and we have its location. But we want to know only the x-axis value of it. So we can press Shift A and search for a separate XYZ node and plug that in so that we have the x-axis, which is now a floating point value. Now we can compare that by pressing Shift A and searching for a compare node. And we want to compare this x-axis value with the x-axis location of each point of Suzanne's vertices. So let's press Shift A, search for the position node. And now let's press Shift A and search for another separate XYZ. Now we have the x-axis location of every point of Suzanne. Now, if we just check for greater than and plug that into the selection, now you can see we can simply take this empty and press GX and move it, and Suzanne will slowly appear or disappear based on which direction you move it in. So let's go ahead and just switch off overlays and then press GX, and you could actually animate this and have Suzanne appear in a really cool way or disappear based off of your requirements. So I think that is a really easy way of doing something like this. It's just a few nodes and you get a really cool effect. If you want this to be even smoother, you could press Shift A and search for a subdivide mesh node or subdivision surface, plug that in and just increase the levels up to something like 3. And now you have a really smooth Suzanne. Now, if you were to take the empty and just move it across the x-axis, you can see a smooth transition of it slowly appearing or disappearing. In fact, if you don't want this transition to be a perfectly straight line, you could add in some amount of randomness to it as well. So how would you do that? To add in some randomness, you simply take this, press Shift A and search for a math node. Now over here, let's add in some amount of randomness. So let's search for a random value, plug this in right over there. And now let's just change this min to a value of minus 0.2 and a max to a value of 0.2. So now if you were to take the empty and just press GX, you see there's this really cool animation of it slowly coming in, or fading out. So I think it's really cool the amount of control that you have when you actually understand what geometry nodes is and how you can use it. Very few nodes and really cool outcomes. So with that, let's actually go ahead and create our next geometry node tree to understand rotations. So let's press Shift A and search for a mesh cone. Let's go ahead and create a new geometry node tree for it. Now, let's say I want this cone to point towards some empty. First thing that I need is the location of the empty. So let's drag that empty in. Next, you see the empty has a rotation socket. So you might be tempted to use that. So let's actually see what happens. If we press Shift A and search for a transform geometry node, plug that in right over here and take this rotation into the rotation, you see it doesn't make any difference. If we were to move this empty around, there's absolutely no difference. And that's because this is actually telling this rotation to take on the rotation of the empty. Now the empty has no rotation, so this has no rotation as well. If we were to now rotate the empty, you can see how rotating the empty automatically rotates this particular cone. So that could be something that you might want to use in some situations, but that's certainly not what we wanted right now. We wanted the cone to point to this particular empty. So let's actually just press Alt-R to clear its rotation. Now, instead of using the rotation of the empty, what we're going to do is we're going to find out the location of the empty and point this in that direction. So how do you do that? You actually use something called an align Euler or align rotation to vector node. So what this does is, remember, the location is actually a vector that goes from the origin to that particular object. So that's the direction. Then we simply want to take the z-axis of this particular object and align it to that particular vector. So let's take this location, plug that in as the vector. We know that the z-axis is the top that we want it to point towards. So we keep this at z, and now we get this rotation that we can plug into the rotation. And now you see it's plugged in and pointing always towards the empty. If we were to now move this empty, it will always point at the empty. So that is something that's super cool, and you can actually use this for so many cooler animations as well. But let's take this one step further. Let's say we wanted to take into consideration the rotation of this empty as well. Maybe let's do a different example that explains that even better. If you tap X and delete this and press Shift A and search for a text, you'll see you can add in a geometry node modifier to the text object as well. Now, if we were to transform geometry and rotate this based off of the camera, it's always going to point towards the camera. So let's do that. Let's take the camera info, plug that in, and simply take this rotation, do the exact same, which was align rotation to vector. The vector is the location, and now let's plug this into rotation. Now, if you were to go into the camera view, you see no matter how you move the camera, the text is always pointed towards the camera. However, the rotation of the text is not really accurate. At least it's not readable, because right now it's upside down. Even though it's pointed perfectly to the camera, it's upside down. So how do you take care of that? In that case, you have to take in the rotation of the camera as well. So let's plug this rotation of the camera as the base rotation for the text. And now you see the text is always going to be pointed at the camera and readable, no matter how you move the camera. So that makes it really easy to keep text readable. If you did not have this rotation, you see sometimes it's just impossible to read the text when you're in 3D space. So that's why by doing this simple change, you always have it readable. So now if you actually see, if you zoom out, we can't actually see the text because it becomes too small. Similarly, if you zoom in, it just becomes too large. So maybe you would want that to also dynamically change based off of how far the actual camera is. So we could do that as well. What you would do is press Shift A and search for a vector math node, change this vector math to length, plug this in over here and use that as the scale. But of course it's a little too large. So let's change this from length to scale. And now let's just reduce that to a readable value. Let's go with the value of maybe 0.05. And let's say that is my text. Now, no matter how far back I zoom or how close I zoom, we can actually see that by zooming in and zooming out, the text remains relatively the same size within my camera view. So that is something that's super useful and can be used in explainer videos and things like that. In fact, if geometry nodes had come out when I used to make my PhysiFacts videos many years ago, it would have been really useful to be able to control that so easily. But since we are dealing with text, this brings me to another useful data type example, which is the text or the string data type. So we could just use this string and a strings to curves node and simply plug this in just like that, so that you have control over what you actually type as well. So now you see you have the text. You can change this up to be whatever you want right over here. So that's something that I would say is extremely cool. And now you understand how the string data type contains essentially string data. It could be just text. It could be alphanumeric. So you could say 2727YT and it would just show 27YT. So that's the string data type as well and how you could use it. If you want another example of the string data type, you can definitely check out videos in various playlists of mine, as well as linked in the description if you want some more examples. So now that gets us to another data type, which is the image data type. And within this image data type, I will also talk about the color data type as well, because most of the time they go hand in hand. So let's go ahead and create a new object. Let's press Shift A and search for a cube, and let's create a new geometry node tree for that particular cube. Now let's remove the group input and create our own geometry, but we want to create that geometry based off of some image. So let's actually press Shift A and search for a grid, and now let's plug this in over here. Now, how are we going to change this grid based off of some image? So let's press Shift A and search for an image. Now we can go ahead and open whatever image we want. So in this case, I've opened up my logo, and all of the information from this is being stored as an image over here. Now, what could we do with this? We could actually use something called an image info node that will help us access the data from this particular image. So we can just plug that in. We could have opened it right over here, but this allows us to change it out over here, or even use this as an input from the geometry socket as shown before. Now this gives us the width and the height of the image. So if we were to simply plug this into the size X and size Y, we get the exact size and correct ratio for our image. Luckily, our image was square, so it remains square, but that's actually very useful for non-square images. Now you know the exact ratio. You don't have to know the ratio, but you can directly get it right from the image data over here. Similarly, if it was a video, you have the frame count and the FPS and things like that. That looks pretty useful, but let's go ahead and now increase the number of vertices to also match the number of pixels that we have in the width and the height. So now we have the right number of vertices as well. Next, what we're actually going to do is use this same image to get the color values from it. So for that, we search for an image texture node. Now this image texture is going to take this image as an input. So you can see we can plug that in right over there. They have the same apricot color, and we get the color information. Now this color information contains 4 values: the red, green, blue, and alpha. Now that can also be changed to hue saturation value or hue saturation lightness. So let's actually separate out those values. Let's press Shift A and search for a separate color node and plug this color in just over there. Now you can see we have the red, green, and blue. If we wanted just the blue, we could just use it from here. In fact, let's do that for the time being, and then we'll go to something else. So let's press Shift A and search for a delete geometry. And let's say I want to delete everything that does not have blue. So if the blue is less than, so let's compare, if the blue value is less than, let's say something like 0.05, then we would want to delete it. So let's plug that in right over here and delete it right over there. So now you see, we instantly got all of the blue areas of my image. Now, granted, most of my image is blue, so it works. However, we could have also changed this to HSV and used the value and seen if the value is less than something, then it gets deleted because the background is black. And this gives us a little bit better control, and we can even get a nice animation of it actually appearing just like that. So you see how we created geometry, and we can actually animate in a transition for this geometry based off of just the image data that we have right over there. So let's say I like this. We can give this some thickness as well by pressing Shift A, searching for an extrude mesh, plugging that in right over here. Let's uncheck individual and just increase the offset scale. And now we have a 3D mesh. Granted, yes, this is very jagged, but maybe you're making something in a blocky style, Minecraft style, all of this works. You could further change this to use some sort of subdivisions and things like that and make it even better. But for the time being, this is something that you could do. You could use even more high resolution images to make this even more of a higher resolution, or you could press Shift A and search for a subdivision surface and plug that in right over there. Now that will smooth it out quite a bit as well. So these are all different use cases of the color data type, the image data type, and so on. So we're pretty much done with most of the data types. I'm leaving the matrices data type for a separate video that will be released later on. I believe the menu data type we've already explained in the last video and given the only example that I can think of. So the only 2 data types that remain are the collection data type as well as the material data type. So let's give an example of the collection data type. So let's go ahead and just hide this. Let's create a new collection of, let's say, 10 different objects, or just a few. Let's add in cubes. So let's just move that there. So that is a cube. Let's press Shift S cursor to select it so that the cursor is here. Let's add in maybe a cylinder. Let's add in a torus, and let's add in a cone. Now, these are different objects by themselves. we can go ahead and select all of them and tap M to create a new collection. Let's call this objects and just have that as is. Now, back in the origin, we can add in a new geometry node object. So let's just create a cube and click new. Now let's remove this group input. And let's say I want to instance all of the objects from my collection called objects everywhere along a plane. So let's create a plane. Let's press Shift A, search for a plane, or in fact, let's do something even cooler, right? We had this particular geometry that we created. Let's actually remove this extrusion and subdivision. And now we have this. Let's just scale this down by a bit. So let's search for a transform geometry, plug that in right over here and scale it down quite a bit. Now, let's say I want to make this object out of all of those tiny instances. So let's press Shift A and search for a distribute points on faces node. So the moment we take this, it takes this mesh value, it sees where the faces are, and it just distributes some points based on the density and seed onto those faces. So now we just have a bunch of points. Now on those points, let's press Shift and search for an instance on points node. And for the instances, instead of plugging in a specific object, we can search for a collection info node. So now we can use this particular collection, which is white. So in fact, we can just search for a constant collection and select the collection from here, which is objects. Now we can go ahead and separate children. We could reset them, we could use relative, but we want to use the original so that they all appear from their origin at the center. And now this can go in as the instance. Now let's go ahead and just choose pick instance so that only one object is taken at each place. And let's just scale these down quite a bit. And now you see you have my logo made up of all of these smaller instances from whatever we put in the collection. Now we could have put in images in the collection so that we could create a larger image made from smaller images, or we could use, different shapes, specific shapes, so on and so forth. You can make this even better by randomizing the rotation. So let's search for a random value node and changing this from float to vector. Now let's plug this into the rotation and let's change this min to -pi and have the max as pi, which means it goes through one full rotation. So now you see you could have some cinematic shots like a close-up that starts off from just these random objects. And then as we zoom out, the random objects form, a logo. So that's actually something that's really cool. If you're into recycling plastics, maybe you could have plastic bottles that eventually form this particular logo. So that's actually an example of how you can use collection info or the collection data type. The last data type is the material data type. So that's, I feel, mostly self-explanatory. If you press Shift A and search for set material, all this does is it just chooses which material from this material panel you would want to select. So over here, we already have a couple of materials. So the default material for now is already present, but you could create new materials. You could have multiple of them as well. And you can just select one from here. So that would be the material data type. And you could use a constant material. You can use this as an input socket to be able to select it from the modifier panel as well, and just plug that in so that it takes on that particular material. So again, this is used in almost every single geometry node tutorial out there. So you will get a good example of it in every single video, but that's actually about it. With that, I hope the combination of the previous video and this video gives you a concrete understanding of geometry nodes and how to use all of the different data types. If you have any questions or queries, comment them down below and I'll definitely try to respond to as many of them as I can for as long as I possibly can. If you have any suggestions or requests, let me know and I will take care of those. I just started working on creating the first short film that I will be creating for myself and my viewers. I've been thinking of a certain storyline that would help me actually realize this vision. It's not going to be a great short film, but I've been making short films for different clients and haven't been able to make one for myself and this channel till now. So I'm going to focus on creating that for the next couple of days. And I really hope you're all going to like it. So I'm really excited for that video and I really hope it comes out great. But until that video comes out, thank you so much for watching. Keep creating and don't forget to stay creative.